Okay, let's go ahead and start. I'm impatient to hear to
Yeah.
start our seminar. So hi everyone, welcome to our series. My name is Kazi. I'll be moderating the seminar today. And today we're going to welcome Dr. Melissa Marie Gervais to talk to us about impacts of projected Arctic sea ice loss on the daily weather patterns over North America. I just want to remind everybody that the seminar is recorded. And at the end, we will have a couple minutes for Q&A. You can raise your hand, you can unmute yourself and ask questions. So I'm going to go ahead and pass it on to Ralph to introduce our speaker.
Yeah. Hi. Yeah. We're very excited to have Melissa here. She's an assistant professor at Penn State, Department of Meteorology and Atmospheric Science, and also, I guess it says co-hire of the Institute for Computational and Data Sciences. Been at Penn State since 2018, I think. And gotten her advanced degrees from McGill University in Canada, Toronto. She studies a lot of coupled climate, ocean surface and atmospheric dynamics. Let's see. Also, she won a prestigious NSF Career Award in 2023, focused on this topic. And I'm going to turn it over to her. I think this is a really interesting topic. I think people think about climate change in terms of like, oh, it's hotter today or colder today or whatever, but I don't think a lot of people think about the effects on the weather pattern. So I look forward to the talk.
Great. Well, thanks so much for the introduction. And actually, with that career award, the education component is actually all about how we communicate climate change. And I think understanding climate change from this synoptic kind of weather perspective is actually, I think, a really useful tool. So just kind of tying into what you were just mentioning. Okay, so before I kind of get started in the heart of the talk here, as I was preparing this, it reminded me of an experience I had back when I was a grad student at McGill, where I did some outreach work in Delaunay in the Northwest Territories. And we were doing some outreach working with the local community college and teaching about weather and climate alongside elders in the community. And one of the things that by the end of the second week, the elders said to us said to the students was, you're going to have to, our traditional knowledge is no longer working the way it used to, and you are going to have to start listening to scientists like this in terms of understanding the weather in Delaunay. And they also rely heavily on an ice road that goes across Great Bear Lake, this is where Delaunay is. It's right here in Great Bear Lake, so just south of the Arctic Circle. And so this is a community for whom the impacts of climate change and Arctic amplification that I'm going to be talking about really matters. And in the research I'm showing, I'm talking a lot about the mid-latitude connections between Arctic sea ice loss and daily weather patterns. But I do think it's really important that we kind of keep in mind that there are communities that for whom this really matters and for whom I think we tend to not study this as much. So anyway, it was just something I was thinking about as I was putting this together as some context. And then the other aspect of that is that these elders who've been studying and thinking about the weather in the region for a long time, we're already starting to notice a change, which I think is pretty powerful, or at least it was to me. Okay, so with that, I just want to dive in here. So this here is a map of the current Arctic sea ice conditions, just to sort of orient ourselves. So anywhere where it's white, we have 100% sea ice cover, blue is 0% sea ice cover, and then anywhere that kind of hits this 15% mark, we would consider that to be ice covered. So it's March right now, so we have a lot of sea ice cover. And I want to point out a few areas here. So for example, in Hudson Bay, as well as the Bering Sea, we do have sea ice cover in the wintertime. In the summertime, that will not be the case. So there's a big seasonal cycle in Arctic sea ice. So this figure is a pretty classic figure generated by the National Snow and Ice Data Center that provides the sea ice extent. So that's anywhere here where sea ice covers 15% of the area. We consider that to be ice covered. And so this number is the extent in millions of square kilometers of Arctic sea ice. So in the gray line here, you have the median from 1981 to 2010. and we have our interquartile and interdecile ranges in the shading. And then a couple of, I chose a couple of specific years to highlight here. 2012 is the record minimum in September of Arctic sea ice. 2023 was last year's. And in the blue line, we have a fairly recent view of where we are this year. So kind of straddling that lower edge here in terms of sea ice extent. So one of the things I want to take home here is that there is a very large seasonal cycle. Sea ice is lowest in September and highest in March, which is where we currently are, March and April. Now, a lot of what we think about when we think about sea ice loss is we often see pictures like this, which is the annual minimum Arctic sea ice. So here, this is going from year to year, and the extent is kind of plotted here interactively as it goes. And we can see, so one thing I point out here, Hudson Bay is sea ice free in September already. And as we go, we can see that the annual Arctic sea ice minimum area is declining rapidly over the historical period. So we're actually able to observe this happening already. And so this will go all the way through to 2022. So we can think about what we've already seen, and then we can think about how that will change in the future. And so here are future projections of Arctic sea ice. On the right-hand side, we have September. So the observations here are in black. The climate model simulations, this is from the CMIP6 climate model set of simulations. The historical period is in gray. You can see that the climate models are actually doing a pretty reasonable job capturing the sea ice. So what we're looking for is not that the sea ice looks like this mean here. We're looking for the observations to be captured by this broad cloud of historical runs. And then here we have different projections of what we think the future might look like. And so there are three different scenarios plotted here. And then this is looking at September. And so you can see that, and this line here is when the sea ice is considered to be roughly ice-free. So we can see we can hit an ice-free September sea ice in 2050 for the higher scenarios. And in some scenarios, it doesn't quite reach there. So this is what we often think about is September sea ice loss, because that's when sea ice loss is greatest. But sea ice loss in the winter is also really important. So this is the sea ice area in March, same plots. And you can see that in March, we also expect a really large decline in Arctic sea ice. And it is very dependent on the scenario, again, how much decline we expect to see. Now, the reason I'm kind of pointing out the impact of sea ice loss in the wintertime is because of how it impacts, winter sea ice loss impacts the atmosphere. So even though sea ice loss is greatest in the summer, the impacts on the atmosphere are greatest in the wintertime. And so this is a really great schematic by Taylor et al. 2022. I'm just gonna walk through it here just to give us a basic understanding. This is kind of really high level viewpoint of how all this system works. So in the summertime, we have incoming solar radiation, shortwave radiation that's coming down. The sea ice itself has a very high albedo, so a lot of that is reflected back into space of that incoming solar radiation. And then in the wintertime, we have polar night. So in that trip I was talking about at the beginning, we were just south of the Arctic Circle, and it was during January and February. So we had just a few hours of twilight every day. And then if you're actually within the heart of the Arctic, you have complete darkness. During the nighttime, during the winter time when we have polar night, we have this really strong temperature inversion at the surface where it's a lot colder at the surface. So this is the normal conditions here. And this is kind of a schematic to show what happens when we have sea ice loss. So this is in the summertime where our sea ice edge has retreated. We have that incoming solar radiation, But because our ocean has a lower albedo, we're able to absorb more of that incoming solar radiation, and that acts to heat up the ocean surface, and it also acts to melt some of the sea ice, more of the sea ice. And then come winter time, the atmosphere is colder than the ocean, so we have a lot of latent and sensible heat flux that are fluxed from this warmer ocean into the atmosphere, and that leads to a warming of the atmosphere, especially near the surface, but extending above as well. And so we see an erosion of that inversion layer that existed here, and much warmer ocean and atmosphere. And so that's kind of the basic concept of how sea ice loss can drive Arctic amplification. So Arctic amplification is a phenomenon where the Arctic warms faster than the global mean. And this is a very robust impact of Arctic sea ice loss that we can see in the observations and that we can model with our climate models. There are additional feedbacks and processes as well that are important when it comes to Arctic amplification. But we can get this, with models where we artificially modify the sea ice or we remove sea ice. And kind of going one step further, so this is kind of the mean dominant effect is Arctic amplification, so more warming in the Arctic compared to the globe or the rest of, or the lower latitudes. In addition to that, there's been a lot of research done on the impacts of the mean circulation as well. And this is a little bit trickier, but there has been some model agreement that we might expect a weakened Aleutian Icelandic low, an intensified Aleutian low, and certainly an equatorward shifted and sometimes weakened zonal mean mid-latitude jet when you compute the zonal mean and you look at the jet. So Screen et al. Had a look at several models, not all the models that are available. And those were some kind of general takeaways, although it will be model dependent. Now, this is how it impacts the mean circulation, but what we experience as people is the daily weather. And so this has actually been the subject of a lot of research as well, is how the Arctic connects to the mid-latitudes and how it impacts the variability in the mid-latitudes. So there have been several review articles that have been conducted, and a lot of this has been looking at this in the observations. And one review article in particular here, in terms of those historical changes in atmospheric variability, it's a little bit unclear the role that sea ice loss plays. When it comes to looking at future Arctic sea ice loss, where we have a larger, it's a larger forcing because you have more sea ice loss, there have been studies that have shown impacts on atmospheric variability that are pretty robust. The first is a decrease in the variance over North America, specifically in the temperature. And another one is a decrease in intensity of colder outbreaks that impact the mid-latitudes. But one of the holes here is that although we can identify statistically that there's a decrease in variance, because of how these studies, because of the methods that we use in these types of studies, it's really hard to probe the mechanisms that are actually responsible for these changes. And so that's actually the subject of our paper, which will be the topic of the talk today. So this talk is really centered around our recent paper that came out. I forgot to mention this at the front, it was in my slide, but this research was conducted with Lantau Sun and Clara Desser. So our research question was, how does sea ice loss impact daily weather patterns over North America? And what are the mechanisms that are responsible? So the approach that we're using here is we're just using one fully coupled climate model, and it has future Arctic sea ice loss. So 2 experiments with and without future Arctic sea ice loss. And then kind of, I think the part of this that is allowing us to really answer that question of why is that we characterize the daily weather patterns using a method of self-organizing maps, a machine learning method. And from that, we're able to actually look at what's going on with these different dominant patterns over North America. So to kind of continue on with the methods here, so the model simulations are from the whole atmosphere community climate model. It's fully coupled, so it's interactive ocean, has 66 vertical pressure levels, and it's a little bit lower resolution at 1.9 by 2.5 degrees. For both experiments, the radiative forcing is constant at the year 2000. And we'll have 200 years of simulations to work with because the first 100 years are disregarded. So there's two experiments. The first one is a control. So in this experiment, the sea ice is nudged towards the ensemble mean of the sea ice in a just loosely running climate model over the historical period. And it does have seasonally varying conditions. So there's a long wave radiative forcing that's applied to make sure that the sea ice looks like what it looks like in 1980 to 1999. And then in the experiment, the sea ice is instead nudged to the projected 2080 to 2099 sea ice cover. And if you want more details about the method, it's covered in this paper by Desser et al. Okay, so first we're going to talk about what the mean impacts of sea ice loss are in these model simulations. So the first is looking at the monthly mean sea ice extent, kind of that National Snow and Ice Data Center figure I showed you earlier in the observations. So here we can see that in our control simulation and then in our experiment. And you can see that we do see sea ice loss in all seasons, and it is greatest in September. And then the figure on the right here is the December, January, February mean differences. And so we're seeing that as a spatial map. And we can see that sea ice loss in the wintertime is really concentrated in these peripheral seas. And I've kind of been highlighting Hudson Bay oftentimes because it'll end up being really important for the work that for our results that we found. So we can see a loss here and then along these marginal seas as well. So in terms of the mean differences in the atmosphere, the first figure here is the seasonal mean differences between the experiments in potential temperature at 850 hectopascals. So as we expect, we see a warming in the Arctic. So we see Arctic amplification in our potential temperatures. And this is the geopotential heights at 500 hectopascals. And I should note in all of these figures and in most of my figures in my talk, stippling denotes places that are not significant. Everything else is a significant difference. So along with warming, we expect a rising geopotential heights. And then looking nearer the surface, we have sea level pressure here. So I should also point out here that the black lines are just the seasonal mean within the control simulation to give you an idea of what the climatology looks like. And then the differences are plotted as colors on top of that. So here we have the Aleutian low, and you can see that the sea level pressure difference between the two is such that when we have sea ice loss, we deepen that Aleutian low. And then also very notably, and again, notably because this will be important later on, we see a localized decrease right over the regions of sea ice loss. So for example, here we have sea ice loss that we saw before over Hudson Bay, and we see a localized decrease in sea level pressure. So this is an expected response that is just a thermal low developing or a thermal low pressure difference developing because of the difference in the heat fluxes that would be there with and without sea ice loss. And then finally, here we have the wind speeds on the dynamic tropopause, which is defined as the two potential vorticity unit surface. So this is this is basically, the tropopause is a really nice place to look at the jet because as the troposphere rises, the tropopause will the dynamic tropopause will rise with it. So you're always capturing where the jet would be maximum. And so we can see an elongated North Pacific jet and as well as an equatorward shifted North Atlantic jet, which would be consistent with the literature. Okay, so that orients us as to what our mean state looks like in these specific models. So now I'm going to talk about how we found our large-scale patterns of circulation. So the first thing we needed to do is isolate changes in variability. So in order to do that, we took the 500 hectopascal geopotential heights, and for every day, and we removed the daily climatology computed separately for each of our simulations. So we have a daily climatology for the control. So every January 1st, we remove the daily January 1st climatology from the control simulation. And then for the experiment, every January 1 in the experiment, we remove the January 1 climatology in the experiment. So this removes the mean difference between the two, as well as any seasonal differences, changes in seasonality that might be occurring. The next step after we've computed these anomalies, this really gives us the departures or the patterns of variability, is identify the dominant large-scale patterns. So we do that using self-organizing maps as a classification method. So I'm going to take a little detour just to talk about SOMs, because this isn't something that necessarily everybody is familiar with. And if anybody has questions about this at the end, I'm really happy to explain SOM. I love talking about it, so please feel free to ask questions. So SOM, self-organizing maps, is an unsupervised machine learning method. So you give it inputs. In this case, it's going to be patterns of Z500 anomalies over North America. So daily patterns of Z500. And the SOM is actually going to determine what the dominant patterns are from this. We don't tell it what the pattern should look like. It uses competitive learning and self-organizing. So the actual algorithm will identify the patterns, and it self-organizes in that similar patterns will be located close to each other. And then lastly, it does make it assumes that the data exists on a continuum. So what that means is that we don't have patterns where we have, you know, positive anomalies here and negative anomalies here and nothing in between, which is great because that's what the atmosphere looks like. The atmosphere exists on a continuum. And so it tries to best approximate that distribution. This is just a schematic that I love using. It's from Wikipedia, but I love using it. Each of these little vertices here kind of represents one of those large scale patterns that we're training. We start off with random data. We then train by saying, okay, I'm going to take that first day of Z500 anomalies, and I'm going to find which large-scale pattern is the closest match. And then after it identifies that closest match, it modifies this map to look more like the data. And it doesn't just modify the one that's the best, the closest match. It modifies the ones around it. So it just kind of sucks itself towards that cloud of data. And by the end of the training, you're really approximating that full distribution of the data. So to kind of put this in, I often get this question, I think because in our field, a lot of people use empirical orthogonal functions. So I added this slide to kind of give you the comparison between the two. This is something I actually use when I teach this in my grad practical stats class. So this is just some simple test data, bullseye patterns that are positive and negative, and bullseyes that are shifted, you know, to the northeast and the southeast corner. And I just created this data. It just repeats this data over and over again. And that's the time series of what the data looks like. So an EOF, the goal is to maximize the variance that you're representing. It does make a pretty big assumption that the patterns are orthogonal, and that's not always true and not often true in the atmosphere. And it also does require that the data be stationary, i.e. it's not changing over time, although it is often used in a non-stationary context. So for this data set, the first EOF looks like roughly like a bullseye, maybe a little bit warped. And this explains 93% of the variance in the data set. And then the second EOF kind of is, I think, trying to capture a little bit of this and a little bit of this, but it doesn't actually look like any of the patterns that occurs. But this is a really useful tool, and it can help you to understand and recreate the data that you see. This is how SOM handles it. So SOM learns through training on the input data, and it spans that data space. And it does assume it exists on a continuum. This data set does not exist on a continuum, so we'll see that here. And then the other part of it is, and this is kind of the downside of SOM, is that it does have a large number of free parameters. And one that is always really challenging for people is that the fact that you have to choose how many nodes you use. So we always test a bunch of different SOM sizes to come up with the best size for our problem. So this is what happens when you put the same data into a SOM. And what you see is this pattern here is perfectly represented over here. This pattern here is really well represented here, et cetera. And each of these occurs 25% of the time, which is how often each of these occurs. And because the data doesn't actually exist on a continuum, we actually have these nodes that kind of span the difference, but no data is ever assigned to them. This doesn't happen with real atmospheric data. You always have nodes that have data assigned to them. But anyway, I hope this preemptively answers some questions about the difference between EOF and SOM. I think one of the really strong pluses here for the applications that I'm using this for are that you really are finding patterns that look like the data that you're using. And so that allows us to do some really great compositing work that you're going to see here. Okay, so after we identify all of these different patterns, every day of data is assigned to the closest map node or the large scale pattern that is the closest to that day of data. And that allows us to do something really interesting. We can look at the frequencies, which I'll denote as an F here throughout the talk, that's how often the best match unit provides. So the best match unit provides us information about how often each map occurs. And so that's telling us how often that large scale pattern is happening. And the second thing we can do is we can compute composites. So we can take every day that's assigned to a map node and average it together. And we can do that not just for the data that it's trained on, but for other variables as well, which is what I think allows us to really look at the processes that are occurring. And so this is the SOM that we created here in this paper. So this is a SOM of Z500 anomalies. And the colors are the SOM and the black lines are the climatology, are just the Z500 mean in the control simulation, just to give you a sense of where the climatological ridges and troughs are. So I hope that you see some patterns that you would expect and that you're used to seeing in the atmosphere. We see positive PNA-like patterns up here, negative PNA-like patterns down here, patterns up here that are AO or NAO-like patterns. And here we see some patterns where we have a kind of a shifted climatological ridge a little bit to the west. Now, this is what the actual SOM looks like. I said that we could do composites of other variables that are assigned to each of these patterns. So here are the composites just in the control simulation of the potential temperature anomalies at 850 and sea level pressure anomalies. And so you'll see a few things here. Here in these bottom right nodes, we see an eastward shifted Aleutian low and warmer potential temperatures associated with that. These two patterns here have much colder potential temperatures at 850. And this one in particular will be one that we'll end up focusing on for reasons you'll see very shortly. So the first thing we think about in terms of how did these patterns change with sea ice loss is looking at, was there any change in how often these patterns occurred? So here I have the frequency, so how often each of these patterns occurs in the control and in the experiment. So for example, this pattern here for 3 is the most common, that's this one here. It occurs 7.6% of the time in the control. And then the difference here, and I only show differences that are statistically significant. So this is the difference in the frequency between the control and the experiment. So we do see some statistical some statistically significant increases in frequencies. Specifically, these patterns here become more common to the detriment of these two patterns here. And just to kind of put this into perspective, although this might seem like a small change in frequency, that means that this pattern occurs 14% more often with sea ice loss. Another thing that a lot of people have wondered about with sea ice loss or talked about is whether or not we have more stationary patterns. So here I have a measure of stationarity by looking at if I'm assigned to this pattern, how many days do I stay in that pattern? So here it's kind of hovering around that 3-day mark in both the control and the experiment. And the differences here, there's only one node that has a statistically significant difference. So in general, across the whole map, there's little change in that residency time. Or you could also think about that as there being no stagnation of the flow with sea ice loss. So that means that there is generally no decrease in the speed of wave propagation owing to sea ice loss. So we might have some patterns that become more common, but we're not really seeing a slowdown of our circulation. Okay, so we have frequency and we also have composites. And the composites are kind of the second and actually pretty important piece of this. So what we're doing here is looking at, so in color we have the, in contours, we have the Z prime 500. So the Z 500 anomalies in the control simulation, composited for each node. So for example, this pattern here has positive Z 500 anomalies over the region that would be typically associated with the Icelandic low. And the colors here are the difference in those anomalies between the experiment and the control. And so one of the kind of main conclusions of this is that many of these circulation patterns are de-amplified. So for example, this circulation pattern was a positive Z500 anomaly in the control, and the difference is a negative anomaly. So we're weakening that, we're de-amplifying that pattern with sea ice loss. And so we see a lot of these are de-amplified or shifted with sea ice loss. So this is the same variable that the pattern was trained on, the SOM was trained on. And now looking at potential temperature at 850, we can see again in the contours, that's the control theta 850 anomalies. So for example, this pattern was associated with really cold temperatures, colder than normal temperatures. However, the difference between, and you can see, you know, throughout the map, a lot of places where we were associated with negative anomalies, the difference is a positive anomaly. So in general, we're seeing a de-amplification of these patterns owing to Arctic sea ice loss. But this pattern in particular is a very striking change. So in the control, just to remind you what that looked like, the anomalies were roughly -2 degrees Celsius. And in the difference, though, is a +4 degrees Celsius change. So that means that in this circulation pattern, we go from that circulation pattern being associated with colder potential temperatures in the lower troposphere to being associated with warmer potential temperatures in the lower troposphere, which is a pretty significant change. So the question is, why does this occur? So here I'm showing on the left is our control simulation, just potential temperature at 850, not anomalies, just the full field, and sea level pressure, full field. So this pattern is typically associated with high pressure over the continent here. And then the experiment, the same is shown for the experiment over here. So if we think about just temperature advection and the temperature change associated with that, we care about, so it's the equation would be -v dot grad T. And so we can see here that kind of considering this little cross section here as an example, we have very large gradient in temperature in the control compared to the experiment. And that difference can be explained by that mean Arctic amplification. And this is not new. This concept here that Arctic amplification leads to a decrease in the temperature gradient, which leads to less cold air advection. So this is something that people have talked about before. This is a thermodynamic effect that would be pretty robust. And most previous studies have kind of identified this as the main factor. But because we've looked at this from this synoptic perspective, we're actually able to see for this specific pattern what the circulation changes look like. And so kind of thinking about or assuming a geostrophic wind, the geostrophic wind is related to the horizontal pressure gradient here across this cross-section. So the change in the geostrophic wind divided by the total geostrophic wind would be proportional to that change in horizontal temperature gradient, horizontal pressure gradient rather, relative to the original. And so here in the control, there's a roughly 12 hectopascal pressure gradient here that's resulting in a meridional southward wind. But within the experiment, this is really reduced to 8 hectopascals. So that's a 30% change in the implied geostrophic wind. And that change in pressure actually can be explained, using this mean sea level pressure difference. So this thermal low here, which we would expect to be pretty robust across many models, when it is imposed on this specific synoptic scale pattern, would be associated with, so this weaker high here is associated with less, a decreased geostrophic meridional wind, and therefore less cold air advection. And so this is demonstrating a dynamical effect of sea ice loss on this kind of daily timescale. And then kind of in addition to dynamical, so we have thermodynamic and we have dynamic effects, we can also see some diabatic effects. So here kind of switching frameworks a little bit and looking at the images, or looking at figures of the control the control anomalies and the difference in those, we can see that there's an increase in total cloud cover and precipitation just downstream of this region of sea ice loss. And that would be expected given if you have open ocean and you're bringing this and you're traveling across now open ocean where it used to be across sea ice, you're going to have a lot of heat flux that allows you, heat and moisture flux that allows you to create those clouds. So that's just downstream of Hudson Bay. So that increase in clouds and precipitation can lead to an increase in diabatic heating, which leads to warming. So this is, some evidence that diabatic effects could also play a role, although we can't really quantify it as easily. Okay, so I've kind of honed in on this one node, and I've talked about some of the mechanisms through which sea ice loss might be impacting this really strongly. I think a really natural question is, well, does that really matter? Does this one pattern really mean that much? So here, one of the ways that we looked at addressing that question was looking at the contribution of individual large-scale patterns to the total change in 850 hectopascal potential temperatures. So for any SOM, and you can, if you're interested in the details of this, you can see a previous paper of mine. We can approximate the total change as the frequency of each of those patterns multiplied by the composite. And so then we can look at changes in the total change here. We can split that up into changes owing to changes in frequency, or how often each pattern occurs, and changes associated with the pattern itself. So for this specific application, the changes in frequency have a negligible effect. And so we're really caring about the impact of the change in pattern. So we can say that the total change, which would be like this image here, the potential temperature at 850 difference DJF difference between the two experiments is roughly equal to the sum of the contribution of the changes in each pattern times their frequency. So taking that as a fraction and multiplying it by 100, we can get a sense of how important each of these patterns are in generating that mean difference in potential temperature. So the sum of all of these is approximately 100. So if each of these contributed equally, they would each have a contribution of roughly 6.6%. And I should point out, anywhere that has stippling, again, is not significant. Anywhere that is missing stippling is significant. So what we see is in this node 1, 2, it's contributing depending on where you are. So further north, contributing in that, 10 to 20% of the total Arctic amplification is owing to this node. And if we think about the mid-latitude extension, it is responsible for roughly half of that. And so this pattern is playing this outsized role in producing that mean change in potential temperature, especially in terms of the mid-latitude extension. So just to kind of wrap all this up, the main conclusions here are, first of all, we are not seeing any evidence of stagnation of the flow with sea ice loss. We do see that certain patterns, specifically patterns that are typically associated with cold anomalies, are becoming more common with sea ice loss. However, kind of countering that, sea ice loss tends to act to de-amplify or shift our ridges and troughs, as well as the associated potential temperature at 850 anomalies. So thinking about this, so basically, in general, we're seeing a de-amplification of the variability, which is very consistent with previous studies. But here we're kind of showing that in a spatial sense. And the fact that this framework was conducted in this kind of synoptic daily weather pattern framework, we were able to get some new insights in terms of the mechanisms responsible. So this allowed us to dig in and show that in terms of the impacts of sea ice loss on daily weather patterns, both thermodynamic, dynamic, and diabatic processes play a role in modifying the atmospheric variability. And then kind of the last point, which hammers home the idea that understanding this from a synoptic perspective can be really important, is that certain patterns, specifically that pattern 1, 2, played a really outsized role in producing the mean Arctic sea ice response. And the last thing I'll note, although we can't actually show this in this specific paper because of the way we've done this, that pattern looks a whole lot like a cold air outbreak. So it does seem like there is a role for thermodynamic, dynamic, and diabatic processes potentially in modifying cold air outbreaks in the region. And that's something, that's part of the future work in my research group, is specifically looking at cold air outbreaks. And so with that, I will take any questions.
Thank you. So if you have a question, please go ahead and raise your hand or just unmute yourself. Everyone has the ability to do that. We do have 2 chat questions that I'll read out loud now. So they're kind of long, so you might want to open up the chat if you can. So first one, could one apply SOM to a set of EOFS plus residuals? E.g., we understand EOFS, but as you say, the EOFS doesn't necessarily look a lot like anything we see in nature. Point excuse being EOFS collapse a lot of data in data space to too many fewer variables, implying that the SOM could be trained more easily faster.
That's an interesting question. You certainly, I think, could do that. I guess what you're saying is take the first EOF and then maybe apply the SOM to the rest of the data set. I'm not sure what you would accomplish over just using a SOM to begin with. One thing I didn't mention, but I think is kind of clear if you look at the simple data that I gave you here, is that if the data is well represented by an EOF, you will get the first EOF, the positive and the negative phase, who knows which corner or which polarity you'll get where, but you'll always get the opposite, the first EOF kind of spanning this part of the data space. And then the second EOF, if it really truly is orthogonal, you'll actually get the second EOF here. So I don't know that you would really gain anything over just applying SOM to begin with, because SOM can give you the same answer, let's say, as the EOF could. It's just more to look, honestly, it's just more to look at. And so that can be a little challenging for people. You're not deciding, one dominant pattern. You're really kind of spanning that data space and really finding multiple patterns. I don't know if that actually answers your question, though.
They can chime in the chat
Okay.
if they want to, or they can unmute themselves if they want to. I'll read the second chat question out loud now. So, is the Arctic warming faster than the rest of the world due to sea ice loss? The warmer Arctic is also due to the fossil fuel greenhouse gases, which causes the wobble in the polar vortex during the winter and probably during the summer also. I guess there seems to be a lot of factors affecting sea ice loss, including the warmer ocean temperatures. Are all these factors in the models? The frequency of polar vortex will increase. Do we get similar effects from a warming equator?
So to kind of answer your question, here we're assuming sea ice is lost because of greenhouse gas emissions. So we're not decoupling those two. Arctic amplification ultimately is a response to greenhouse gas emissions. It's really, I think, a question of where you are in that chain. So the idea here is that you have a positive feedback that occurs in the Arctic. So you have general warming, right, from greenhouse gases, but in the Arctic, when you melt sea ice, you expose more open ocean, so therefore the ocean can warm. So yes, it is also due to warming ocean temperatures. So the ocean can warm, that can melt more sea ice, and that can perpetuate, and then that warmer ocean can heat up the atmosphere in the wintertime. And so you end up with the pattern where you have more warming in the Arctic than the tropics. And there are, again, additional processes like some people have done work on increased moisture intrusions into the Arctic with anthropogenic climate change, so anthropogenic forcing. So I hope that kind of answers that question. But yes, I guess we're kind of teasing out the role of sea ice in particular within that chain of events.
Okay, thank you. Do we have any other questions? You can raise your hand and I can cue you, or you can just unmute yourself or send me a message asking. Oh, the person who asked the first question said that they will pursue you in an email.
Okay, great. Sounds good.
Any other questions? Have a couple more minutes. Okay. Well, unless I am interrupted, I think we can close for the day. Well, thank you everybody for coming, and thank you to our speaker, Dr. Gervais, for giving us this great talk. We'll continue with the seminar series next week, next Monday, as always. Thank you, everybody. Have a good week.
Yeah,
Thank
thanks,
you.
Melissa. Very interesting.
Thank you.